Okay, we are videoing the meeting tonight as well. Richard, I'm going to say hello to Richard because some of us remember Richard from pre-COVID. It's been a long time since he's been visiting us in areas tonight. You've had quite an illness other than COVID. You've been very ill.
I won't go into the details.
No, not tonight. We haven't got it long enough. We're only here for 4 hours. But it's good to see you back, Richard, and hopefully we'll see you in the coming months.
I should be back on my feet by Christmas.
Yes, back on your feet.
As long as they don't mess up the operation this time.
Well, let's hope not. Okay, just before we get underway, why am I standing up here chairing the meeting? With all respect to Colin, he opened the September meeting as the president of the society, as the chair. He finds it very difficult to stand and talk, as many of us can. He's asked if council members can perhaps take turns throughout the session to chair the meeting. It would be a lot easier for him. He's still chair, he's still present, and we recognise that. It's just so difficult for him at times, and I think we need to respect how difficult it was for him in September. He did really well getting through. Unfortunately, he's not here tonight due to illness as well. So we'll start the meeting at 7:15. I think it's fair to say. Gabriel, come in, Gabriel.
Just in time, so just a warning, the meeting will be recorded.
Okay.
Maybe it's happened next 30 minutes.
That's just been a bit louder.
Yeah, so I'll put the recording now. Just sit down with. Oh, you're recording. Mark, step up the folder for us to show the recording.
That's right, yeah. Okay, so it's been a while since I've stood up here chairing the meeting. I've stood up and made announcements about it, so bear with me for this evening. Again, welcome to the Quaker Meeting House. To our members and visitors, it's an atrocious night, and I'm really glad that you all made the effort to come out. I know some of you struggled through the road works and the bad weather. Can I ask you if we turn our mobile phones off or at least mute them? I know some of you may need your phone on for reasons, and you put them on vibrate, on your buzz or whatever. One of my friends here was selling a Philharmonic last night. Orchestra is just about to go. That's on, taps away. It's underway, and someone's phone rings. We can imagine that in the Philharmonic Hall. Yeah. What was the tune at the?
For 5 minutes.
Yeah. Held 5 minutes. Okay. I don't think we got problems with music tonight. So. O to a mobile phone. Just a quick reminder: COVID is still out there. Certainly, last month I'm aware of it from 3 friends, 3 different groups of friends, and it's still out there hitting people. So if you feel more comfortable wearing a face mask, please do. You want to wash your hands, do so, and look after yourselves because it's as if it never happened, isn't it? But some of us are very aware of it. Fire procedures. Can I ask Phil if you would explain the fire procedures, just in case?
Good evening, everybody. The emergency evacuation alarm is a continuous ringing bell, and there are no plans to test the alarm this evening. If the alarm sounds, obviously we need to go as quickly in an orderly fashion as we can. The main exits from this floor are via the staircase, the main staircase that I think most people will come through. There are 2 alternative exits, one adjacent to the lifts through this door, and another emergency exit adjacent to the toilets at the far end of the building. Also near to that exit there is a muster point for anybody who has any difficulties negotiating the stairs in the absence of using lifts. The exits will take you out into School Lane, and the muster point is just down School Lane in the road adjacent to Primark, opposite the Bluecoat Chamber. Church Alley is the name of that, and there we will take a walk using the book. That's it.
Thank you very much, Phil. Apologies for absence. I've got a couple of apologies. Peter Hanna, Gerard Gilligan, Colin Murray, Amy Sanderlands, Steve Southern. I think that's all I've got at the moment. Is there any further apologies for absence? Again? Emma Chapman, thanks. Yep. I did say Colin Murray, didn't I? Yep. And Camellia Usher Galvin as well. New members, do we have any new members? Any? Not yet.
Well, can I suggest we do it at the start of the second half? I think
Yeah.
that's a 2 minute
So
break.
during the break, if we come to the desk, we can sort out all the details on that. Okay. Announcements. Going through to October and November, we have 2 events coming up. One is next Friday, which is based at Martin Mere in Bearscope, and that's one of the outreach events that we've done over the years. To attend as a member of the public, you have to buy a ticket which costs £10. Now, in the past, that £10, we didn't see any of that money as the society, and we volunteered and spent our time there. It was discussed with the organisers, and they agreed to give us 20% of the takings on the night. I don't know what the public get for their £10. If it's cloudy, we can't guarantee a star, but we give them 2 talks, show them telescopes, answer their questions, and basically, hopefully, make their night worth the while.
What time? Not next Friday, but next Saturday, tomorrow.
28th.
28th. What time
Sorry.
on Saturday?
Sorry, it's Saturday the 28th. Yeah, thanks, Chris. Yeah, what time? 7:30, I think. It's on the website, and Mark has sent an email out. All the members should have received an email with all the details, and I'm sure a reminder will go out in the next couple of days. But if you wish to bring a telescope along and help out on the evening, you don't pay anything. You just basically help out on the night. And we do need volunteers for all these events. It's not easy doing it when there's just a handful of you, and it can get busy with the public. Recent events, Court Hay, we had 400 people daytime doing solar observing, really well attended. Cronton Gala Day, we had 4,000 people attend. I think everyone passed our desk as well. And it was a very, very hot day as well. Myself and Chris were very red, weren't we? as these things happen in the sun. So if anybody wishes to help with any outreach events that we do, it would be greatly appreciated. What else have we got? That's up to November. So let's move on. There's no raffle this evening. Newsletter is out, and again, you should have received an email. If you do not receive the email, if you go to the LES website, all the newsletters are there, all the past ones, and they go back quite a way. And it's a great way of seeing what some of the members are doing, whether it be imaging or projects and so on. So I'll move on to this evening's talk. This evening we welcome Mr. Gary Gilbert. He's an amateur astronomer since 1976, which is probably similar to myself, or thereabouts. Well, that makes us 40 odd years old in astronomy.
Something like that, yes.
It's quite scary, really. What else have we got? You are a maths, science and IT teacher. According to my record, is that correct? My mum said she never had eyes in the back of her head. Well, maybe I do, but there we go. So the evening talk is the Drake equation. Is there anybody out there? Has there anybody not heard of the Drake equation? Okay, I first came about this in the 70s, and it was pretty heavy going. I'm curious tonight how it goes towards the end, because I'm sure things have changed. But we'll see. This theory, Carl Sagan on Cosmos discussed this back then, and our technology's improved and so on, and maybe the formula's changed as well. We'll see. Okay, we'll be taking a break around 8:15 or thereabouts, and at a convenient point for yourself, of course, we'll work that as we go along. Okay, so without further ado, can I ask Gary to start our lecture, and can we welcome Gary, please? Thank you.
As it says, 1976, sister bought my first small white Dingo telescope. Absolutely rubbish scope, but I managed to look at something through it, and there I am. I'm hooked on astronomy forever. Still am. And just before Voyager decided to go and take them fantastic photographs, which a telescope can never beat. So I'm glad I did it before the technology beat me to it. So yeah, I've taught math, science and IT up to the higher levels for about 20 odd years. And I did my first astrophotography in about 2003 from what I call my home dark site, which had the nearest street light 3 miles away. than near a street light. So I loved observing from that particular location.
No. Lost everything.
Lost everything. Give it a few seconds.
That's better.
Fine by me. That's cool. Yep. This is who the talk is about. The Drake equation. The Drake equation is unchangeable because, quite simply, there it is roughly written out on the board, and we're going to go through every element of that particular equation and look at what we've done and what we're going to do and where we are with them currently. And that's every single probability or count for things that will give the answer to the equation. You can't add or take anything away from that. And it just gives someone like me a good excuse to talk about quite a wide range of science, because it doesn't just cover the obvious. And then basically I can do lots of segues into it, and it looks at Sagan and Pioneer, because this man, along with Carl Sagan, designed the plaques to go on Voyager and Pioneer. So this man was well known in his day. He started off as a radio astronomer, which is why he kind of did this, but then everyone in the late 60s, because of Jocelyn Bell, went into pulsars, and he was one of them. So that was mostly what he did to the end of his career. So that was in 1961 he created this equation, and I probably became first aware of it in about the 70s as well, in the mid to late 70s, when it just first became knowledgeable to me. That's the equation. You don't need to read that because I'm going to go through each element of that separately and say what each one is. But they're all the points, and they're all the counts, and they're all the probabilities and the fractions. And what it's really about is that. Quite simply, how many are there in our galaxy? Okay, it's just a number. It comes up with a number, this equation, and we'll discuss the number that some of them came up with later. So it's relating to just our Milky Way. Problem is, I always start with this, a couple of my photographs actually there, the other one was my photograph as well. I start with the most stupid, obvious thing in the universe, because the probability of life, really, it's my favourite slide. Because I'm looking around the room and you're all still awake. So the probability of life is 1. It cannot be argued, here we are. That's just in the Milky Way. Let's extrapolate. That number's probably an underestimate of 2 trillion, so it's only an order of 10 different, but I've seen 2 trillion mentioned a few times as well. So pick a number somewhere around there and you're probably about right. This thing can be applied to any galaxy, pretty much any galaxy at all. But size is obviously a key element, and some of the numbers change between galaxies. The first most important number, the easiest one to be honest, the rate of formations of stars in our galaxy. Okay, you'd be amazed to know it's only about 4 solar masses a year. You wouldn't imagine such a small number was true. When our galaxy's been here for about 13.2 billion years, you start to add up the numbers, they go quite quickly. When we say 4 solar masses, that does not mean 4 stars. We'll discuss in a minute. Most of them stars are nothing like our sun. Okay, and we'll discuss, often we're talking about 40 stars a year. Okay, and we've aged our galaxy through looking at the older stars and some of the diagrams we'll see later, and we know it's about 13.2 billion years old, and that's just our galaxy, which is about 200 million years after when we think the first galaxies formed. So our galaxy probably formed at the same time all galaxies formed. And we used the clusters of stars to find that age, because all clusters were born at the same time. And if you look at the older star and the younger star within a cluster, which is to do with mass mostly, you can actually age a cluster. Globular clusters are brilliant for it, but open clusters work well also. Where they're all getting formed? Well, you've probably heard recently about our little favourite nebula here, the Orion Nebula, with all the jumbos recently, which are not something that's in my talk actually, but pairs of Jupiter-sized planets free floating in space. So planets don't always form around a star. Quite an important bit of information, which is additional to my talk. That is the Horsehead Nebula, which is about around this star here, just down that side. That's the Orion Nebula, which is that lovely little red patch just over there in Orion. So this is where stars generally get formed. Big clouds of gas, and we form stars every single year. Stars are classified, and this is a very important part of the talk in an unusual way. Our sun fits in this G group here, okay, and it's about 6,000 degrees Kelvin, Celsius you might as well say, doesn't make any difference when it's that big a number. That's the surface of the sun. That's an important fact for planet Earth, as we're well aware of. But other stars go up to 40,000 degrees, and lots of stars go down to about 3,000 degrees on the surface temperature. And you know, when we look at our sun, it's nearly 500,000 miles in radius, and that's quite small for a star. And we'll discuss in a moment, most stars are actually small. Most stars. The biggest one is 2,150 times bigger than our sun. The Stephenson 2150. And that one will be probably one of these B or O stars that's gone supergiant. And to give you an idea, that star would stretch beyond Saturn, just the surface. So we've got our star, which doesn't even stretch anywhere near Mercury, and the biggest star goes way past Saturn before you get to the edge of the surface. So stars are very variable in size, and we'll discuss why some of them are bigger in a minute, because that's really easy. So when we look at stars in general, 99% of stars fall in these last two groups. Pretty much, well, certainly the last three. If you include the Earth's group here, 99% stars fall in those groups in the entire universe. This is looking at the big and the small stars now. It's kind of calling these stars as a bit of an exaggeration. Giant stars and supergiant stars. Our sun, one day, about 5 billion years away, will turn into a red giant. A lot bigger than it is now. It'll stretch probably out to about Mars. And these are quite small white dwarfs, about the size of the Earth mostly. They're quite small stars. Supergiants, a bit like that one I just said, Stephenson, when super hot stars die, they're usually quite big to start with, about 20 times the size of the sun, and then they expand, and they go up to thousands of times the size of the sun, and they go twice as big as what the sun can go, even when it dies. So stars vary in sizes, and we have actually detected planets around the smallest star, which is not on our list here, which is a pulsar. The first ever planets discovered were found orbiting a pulsar. Okay, and we'll discuss that one in just a few moments. Just to give an idea, the white dwarf is a little bit bigger than the moon, 1,500 miles. And when we're looking up at the sky, the most recognisable constellation that most of us recognise, especially about this time of the year and later towards Christmas, is Orion. And this is always a great constellation to look at because it has a good variety of spectral type stars in it. And we're all very well aware of that one over the last few years, Betelgeuse. It's 750 times bigger than our sun, about 20 times more massive. Okay? That star is near the end of its life, but it's only about 10, 20 million years old. Okay? It's a young star in terms of our star, but it doesn't live very long. Okay? And that's a very important consideration in what we're looking at in terms of our ability to create life around the star. Rigel, our little fantastic bright bottom right star there, is 79 times the size of the sun. Its mass is even greater than that of Betelgeuse, so this one's even younger. Okay, you can tell because it hasn't gone supergiant yet. It'll go red if it goes supergiant. On the tack, I use that one there because it's very close to that Horsehead Nebula that we had a picture of before. And that's 20 times as big as our sun, but it's 33 times the mass. That one's not going to live more than 10, 20 million years. Its whole life will be over in 20 million years. So that's part of what we're looking at. And one of the reasons I showed these two slightly different pictures of it is most of the stars we see in those pictures are bright. They're kind of blue stars, basically. And most of the stars we see with our naked eye, especially from Liverpool or Manchester, they're blue stars. Because there's not a single faint star that we can see with the naked eye of the small type, the M-type stars that we'll do a bit more discussing on in a minute. 6 out of 30 of the nearest stars are visible to the naked eye. Just goes, most of the near stars aren't even visible. You need a pair of binoculars, and most of them you need a telescope, to be honest. To see all 30 of them, you would need a telescope. So when we're looking at these, I always remember this lovely little acronym at the top, including the NS, which is RNS, which is a bit outdated now. Oh, be a fine girl, kiss me right now, smack. Please forgive me if you find that mildly offensive. It could be Guy. You could use Guy. It works just as well. But these three gradings of stars are high carbon stars and very low temperature stars, and some of them are barely stars at all. What we rarely consider from M to O in terms of what we would call a star. And that's kind of what we need to go on to and look at. What's a star? Famous diagram. This is the important bit. It's called the main sequence. And every star that starts its life starts there. And if you look carefully at it, at the top end here, you can see a path that goes that way. That's what all stars basically do. They'll go where they are, they slightly move up this during their life, only slightly, and then they tend to go sideways. Because our sun is about there, and it'll go up maybe to here during its life. It will change its spectrum, and then it'll just go into this group here. They tend to go sideways, slightly diagonal, and they follow a path. And if you look at thousands of stars, you can actually see them follow each other in a path, a bit like lemmings. It's great. Okay, you get the idea that they're obviously following a trajectory in terms of brightness and surface temperature. And then obviously our sun will go up to here, and then it'll go right across there and down into this little bunch of stars called white dwarfs. Because our sun's a boring low mass star, it needs to be about twice its current mass for it to become anything other than a white dwarf. So when we're looking at these, we can still consider stars that have died that have planets around them. So they can survive the explosion of a star, which I find quite amazing. Okay, that's the first discovery I made when I started to research this. I didn't think any planet would survive that end expansion explosion of a star. So this is called the HR diagram, Hertzsprung-Russell, and it's just a bit of a map of the evolution of stars. Tells us where it is in its life cycle. So the sun's life cycle, we're really only interested in 1 to 2, because that's where it is now. 3 means it's starting to die. Well, we're not on Earth anymore, and that's when it finally ends its job. It goes right down to number 4 and doesn't do anything for probably 1 trillion years. It just cools a bit. So this is where it starts off as a great big cloud like the Orion Nebula. Big lump of that cloud, a globule, collapses, forms a star, and that slow process, when I say slow, if 10 billion years is slow to you, it's slow. To me, it's like a couple of seconds, because we're talking about billions of years. So the idea is this is actually quite a quick process, 10 million years. It will collapse. And most planets are formed at that stage as well, because planets as we see now from the jumbos are just formed from that same cloud of gas. Many of them will start to orbit the star, okay, and they will be in orbit. And then some of them will fly around a bit like the jumbos have been doing. So that was a surprising find that I found lately, that you can detect individual planets in the Orion Nebula floating around in pairs. It was in pairs that gave it away, to be honest. If it was in single planets floating around, they could have been ejected from a solar system. But pairs would only form together as a pair. And if they were to go through, they would either get separated in a solar system, or they would get grabbed by it. So it's just your basic diagram of how all stars live and die. Obviously, the higher mass ones come in over here and then go up there, and the highest mass ones sort of come in over here and go over to that section where they form supermassive stars. So you need 15 million degrees at the centre of a star for it to start burning hydrogen. Not all stars quite achieve that. Okay, those lowest descriptions of spectrums I gave you don't get that high. And many of us have probably heard of these stars, brown dwarfs. And they're kind of doing a sub-level of nuclear fusion. They're not turning hydrogen into helium, they're turning deuterium into a different form of helium. And deuterium's easier to work with, but it's a slower process, so these stars are very faint. They're still fairly sizable stars, but they're very faint, very cool indeed, because they will last. Not one of them stars has died in the universe yet. If one was born on day one of the universe, it's still alive today, and it's probably still going to be alive for another 20 billion years. Okay, and then it'll start to die. So these stars last pretty much the age of the universe as far as we're concerned. So when we're looking at these, we're trying to work out where these stars fall in and the more interesting aspects of what we're looking at. The next part of Drake's equation, fraction of those stars with planetary systems. Well, gives me a little segue, this one, because I'm looking around and the audience looks a similar age to me, except for a few people. I grew up with Patrick Moore, watching Sky at Night from the age of about 11. And one of the first stories I remember on the Sky at Night to do with this area, it was proposed to be the first planet discovered, is Barnard's Star. And the reason why Barnard's Star was picked as an object is it's the fastest moving star in the sky. So over the course of 2 lifetimes, it moves the distance of the moon, which is half a degree. Over 2 lifetimes, 99.9999% of all the other stars you look at wouldn't move in a pair of binoculars over that time. You wouldn't see the movement. This one's moving fast because it's the second closest star to us, and it's a fast moving star. So Barnard's Star was a bit special, so it was being looked at. Now this poor man here, just need to check if I've got a year for that. Not really. This is what it would do in, what's that, 16 years. It depends on the scale of that picture, but that's obviously about a 15th of a degree, that distance. What some guy did in the mid-60s was this. He took a picture of it every couple of years with a telescope. And this was at the time when they thought one of the ways we could detect stars was if they didn't go in a straight line through space. And because of that picture, he thought he'd discovered a planet around Barnard's Star. Now, unfortunately, the poor man got it wrong. What he did was, he changed his equipment halfway through the filming of the star. So this kind of star here and maybe here, that falls out of line with the other ones that should have done this lovely neat line, wobbled in the picture. It's because he changed his equipment. The idea he had was brilliant, that a star would wobble its way through space because a planet's in orbit around it. And he wasn't wrong in his theory. Unfortunately, his application let him a little bit down. So this was one of the first stars which I was ever told would possibly have a planet round it. Well, it's a double bluff because it does have planets around it, but it's got nothing to do with that picture. It's actually got a potentially rocky Earth-sized planet, about 3.2 Earths, called a super Earth, and it's about 233 days in orbit around its star. You'll realise that is an absolute no-brainer, no chance of it being life later on. So that's Barnard's star, the first one. But the one I liked the best, because it was the first real, absolute evidence in a way, is this one, Beta Pictoris. I think this one was probably around 1990 or something like that. IRAS was a orbiting satellite, infrared, taking pictures of outer space, and it took this picture of Beta Pictoris. And people looked at it and went, what is happening there? Well, it's quite simple. We're looking at it edge on. And its disk of planetary material is pretty much in line with us right in front of the star. And because that planetary material just extends out way beyond its solar system, like it does with ours, because we have the Kuiper Belt and the Oort cloud, we have big extensions to our known solar system. We obviously interpreted that picture exactly as you meant to, which is that's a proto-planetary disk. It might even have planets around it. I didn't do the research and check whether it's got any around it now. It's probably got the data on that one, actually. There's a little additional one I could do with looking at. And that is the first real discovery of the possibility of there being planets around other stars. So that was the first one. And that was in 1984, actually, so I was wrong with the year. So what we need to look at is why this is important. Number of planets, the solar system with an environment suitable for life. Okay, when we say environment suitable for life, we don't mean the planet itself. We mean, where is the planet in relation to its star? Does it have the possibility, with our current understanding of what life likes to live on, to form life? Well, this is the important bit, and you start to appreciate now why some stars are great at doing this and some stars are not so great. There's our sun. This green zone here is called the Goldilocks zone. This is a measure of the frost area. This is a measure of you've just burnt your planet to a crisp area. If you're in that zone, you've got liquid water. The current theory is we need liquid water for life. I'm not totally in agreement with that. Life has some fantastic ideas about how to deal with non-liquid water. Okay, even from steam down to ice. So I'm not 100% convinced you need to be truly in that zone, certainly not for the entire of your evolution. It'd be nice if you were in it for a while. If you look at this M star, which we'll look at in a minute in more detail, look how close the green zone is to the star, because that's quite important, and its frost zone is pretty much on the inside of ours. And then if you look at these A stars that are so bright on the surface, you've got to be a long way away from that star, otherwise you are just going to be frazzled with radiation or whatever. It's going to fry you. You're not going to have life. So you've got to have some limits. Obviously, too close to a star, I don't think there's any kind of life that can survive there. But a little bit further away, I can see opportunities which I kind of will discuss in a few minutes. So what you need to appreciate with this picture is that green zone is completely within the orbit of Mercury. Okay? So if you're not closer than Mercury to that star, you're not in a water zone. And that's basically what we need to be aware of. A quick review. So, hot stars, the OBAs, they're quite short-lived. Now, some of them live as little as 10 million years, which we look at our evolution and go, is that ever enough time for something to evolve? So they're poor candidates. What we're going to look at is, are these good candidates, these cool stars? Okay, well, we need to look at some of the data of those. I mean, I quickly want to go back to a slide that I had on here, which I didn't mention a couple of the key numbers. There's the fraction of all the stars in space that are that type. So look at this star, I'm now considering M, and 3/4 of all stars are M. Okay, these are small red dwarfs. Okay, to brown dwarfs, but red dwarfs is the ones. And then obviously it does just go down and down and down. So these big stars don't really amount to a hill of beans really in the calculation, because there's not many of them anyway. So when we look at our data, one of the reasons why M stars are awful is this. That's just a picture of the Earth with the moon going around it. Most of us already know this because we've all looked at the moon. I hope everybody's looked at the moon. It always shows the same face to us, and it's what we call tidally locked. Okay, now imagine the Earth is a star, and the moon is a planet around that star. If you get too close to your star, you get tidally locked. And there's very little chance of recovery there, because the atmosphere tends to get a combination, well, it tends to turn into one of the snowball planets as one of the options. Because strangely, even though you're facing that star all day long with one side of your planet, the far side does get frozen. And all the water, vapour, and even the methane and whatever, condenses out onto the surface. And that creeps around to the front. And when you do that slowly over thousands of years, you end up with a completely covered ice planet. And ice is quite a good reflector of the radiation, so it doesn't tend to melt on the near side if it's at the right distance away from the star. And it depends on what atmosphere is covering that ice as well. If it's like carbon dioxide, like Venus, it would just melt, because that would just take all the heat in and you would have a hot near side. So tidally locking is a big problem when you're near to a heavy object. You get tidally locked. And that's probably not good for evolution, because it gives you a very small temperate zone around the terminator, shall we call it, of the planet looking at the star. It's the only place you could dream of getting life. And if the planet's rotating a little bit, that makes it very difficult. So tidally locking is a great big problem. And we need to make sure that any really close planet to a star will probably get tidally locked. So we're pretty much saying most M stars are now unsuitable. So 76% of the stars have just gone away. So my calculation now for that is at best 25% or 24% at best. The number comes down, but we are talking astronomical numbers to even begin with. This is our other big problem. This is just a picture of the sun. I think it's 2012 CME, coronal mass ejection, which shows it on the little inside picture, and then you use a special coronagraph, which shows it going into outer space millions of miles away. This is a big driving factor in the habitable zone of any star, because if you were around an M star and you weren't tidally locked, the star's playing basically target practice with you. It's throwing them things at you. Our sun does it to us. We had the biggest CME in about 150 years only 10 years ago. Okay, and it basically sent something like that out towards us. It doesn't matter if it doesn't come towards us so much, but it does matter when it does. Because when we look at the idea of this in, I think it was 1869, two astronomers from Britain were looking at the sun on the same day, and they saw a great big flash, more or less in the middle of the sun. And one of the astronomers was called Carrington. I'm sure some people have heard of the Carrington event. So in that year, you could see an aurora all the way down in the tropics. It wasn't in that year, it was actually 1.5 days later. Because that's how quick that thing's flying away from the sun. It travels 90 odd million miles in about 2 days. Normally it takes them 3 or 4 days. This is so big and so energetic, it's